Yeah, thank you very much for the introduction, and also for, I would like to thank all the organizers for inviting me to this nice event. I want to speak about the relation between quantum field theory and gravitation. So this is based on joint work with Romeo Brunetti, Michael Dütsch, and Katarzyna Reisner. Now, we all know that the problem of relating quantum theory and gravitation is a long-standing issue, around 100 years old, and without a definite solution until now. In spite of the fact that quantum physics is a well-established theory with a lot of nice verifications, in particular also in elementary particle physics, where of course the mathematical status is not as good as in non-relativistic quantum mechanics. Oh, yeah. Okay, thanks. But nevertheless, it's applied with great success to experiments in elementary particle physics. And on the other side, also gravitation is nowadays well established as a classical theory. There's a lot of experimental confirmations, but we have not yet a consistent theory which combines both theories. Now here in my talk, I want to approach this problem from a rather conservative point of view, namely from the point of view of quantum field theory. And so the first step is then to look at quantum field theory under the influence of external gravitational field, which mathematically means that you have to study quantum field theory on generic Lorentzian manifolds. And I will then discuss in which sense this can be also used for including perturbative quantum gravity. So when you start to define quantum field theory on curved backgrounds, in the first moment one might think that this is a very simple problem, because in classical field theory everything is defined in geometric terms, and so it's rather easy to formulate classical field theory on generic manifolds. For instance, in electrodynamics, you just need the notion of differential forms, exterior differential, and we need the Hodge-dual to define the codifferential. On the right? Ah, yeah. So, so you see, you need only very, very few things, just that you have a differential manifold and that you have a metric which is then used to define the Hodge-dual. Now, when you try to do something similar with quantum field theory, you see that the standard formulation of quantum field theory uses a lot of other structures. Namely, you define the concept of particles in terms of irreducible representations of the Poincare group. You assume that there exists a distinguished state, the vacuum, which is defined as a state where all particles are absent. We have as a main physical observable the S matrix, which describes the transition from incoming to outgoing particle configurations. And we use as a technical mean the momentum representation, which is possible due to the translation invariance. And as another tool, we use the transition to imaginary time so that we get a theory on Euclidean space. And when one tries to put quantum field theory on a curved background, you see that none of these features is present. So there is, in the generic case, the group of space-time symmetries is trivial. So there is no useful concept of particles on a curved space-time. Therefore, there is also not a notion of a state without particles, so the vacuum is no longer a valid concept. The transition to imaginary terms, so that you can replace your Lorentzian manifold by a Riemannian manifold, is not possible in general. You cannot do calculations on momentum space, and if you just close your eyes and you write down Feynman graphs, then you meet the problem that there's no unique definition of a Feynman propagator. Actually, these theoretical obstacles are then seen in some effects. What was first observed was that there is a phenomenon of particle creation. So in free theories, you might find the definition, what you call a particle, but then you see that this depends on the choice of a Cauchy surface. So when you change your Cauchy surface, then you get different particle numbers. So you have particle creation from Cauchy surface to Cauchy surface, and actually even infinite amounts of particle creation. So this shows that the particle concept is not meaningful. And there's this phenomenon of Hawking radiation, so that if you look at a collapsing star and you start from a state which is sufficiently regular, then you see that asymptotically the state develops thermal radiation. And even on Minkowski space, you have this problem if you look at an accelerated observer, and then you see some thermal properties of the state, the so-called Unruh effect. So in order to define quantum field theory in a curved space-time, it's important to decouple those features which are geometrical from features which are non-geometrical. So what are the geometrical features? These are field equations. These are commutation relations. So in general, these are the algebraic properties of the theory. And this forces one to use the formalism of algebraic quantum field theory as developed by Haag, Araki, and Kastler. Of course, these so you have your physical quantities as elements of an abstract algebra. Of course, this algebra should admit representations on Hilbert space, but you don't use a specific representation. There is, however, one ingredient of Hilbert space representation which is very important for the structure in quantum field theory. This is the spectrum condition, the condition that the energy is positive. And so what you need in order to do this program is you have to find some local version of the spectrum condition. Okay, so this is the plan of the lecture. So I will give a few remarks on Lorentzian geometry and field equations. Then I will discuss quantization in the sense of deformation quantization. The local version of the spectrum condition is imposed by using some tools for microlocal analysis. And then I will discuss how renormalization can be done in this framework, what the notion, appropriate notion of covariance is, and I discuss this on the example of a scalar field, but then I will indicate how this has to be generalized to include gauge theories and even gravity. Okay, so let me start with some basic notions. So we have a smooth manifold, which we call a space-time, and space-times in my talk are always Lorentzian space-time, so the metric has Lorentzian signature. We have causal curves, which are tangent vectors which are always time-like or light-like. We have time orientation, which is imposed by choosing some nowhere vanishing time-like vector field. And so we can say when a curve is future-directed. And then we define the future of some point x as a set of points y, which can be reached from x by a future-directed causal curve. And in the analogous way, we can also define the path of a point. Now, what is important for the following structure is the notion of global hyperbolicity. So space-time is called globally hyperbolic if it does not contain closed causal curves, and if for any 2 points x and y, the intersection of the past of y and the future of x is a compact set. And the nice feature of these globally hyperbolic spacetimes is that they have Cauchy surfaces, so hypersurfaces which are hit exactly once by each non-extendable causal curve. And they even have a foliation by Cauchy surfaces. So they have a rather simple structure, so they are diffeomorphic to a product of some manifold sigma times the real axis. In particular, globally hyperbolic manifolds are never compact. And the for us, most important feature is that normally hyperbolic linear partial differential equations have a well-posed Cauchy problem. In particular, they have unique, retarded, and advanced Green's functions. Actually, these properties of globally hyperbolic spacetimes are around for quite some time, but the proofs are not so old. The complete proofs are due to Bernal and Sanchez. But you find it already in older books, the same statements. Now let's look at a simple example, the Klein-Gordon equation. And there we have the retarded and advanced propagators as maps from the space of test functions with compact support to spaces of compact to smooth functions. So D is a space of test function with compact support, and E is a space of smooth functions. And they are uniquely determined as the inverses of the Klein-Gordon operator, and by the support condition that the support of delta R F is contained in the future of the support of F, and vice versa with the advanced propagator. Now, what is crucial for the structure is that these two propagators are different. So we have a difference of these, often called the causal propagator and later named the commutator function. And this will be crucial for the algebraic construction. Namely, in terms of this commutator function, you can define a bilinear form which is antisymmetric, bilinear form on the test function space, and which is degenerate, but the degeneration is of a very simple form. Namely, if you this form vanishes if one of the entries is in the image of the Klein-Gordon operator applied to a test function.
Sorry, doesn't it look symmetric, the Laplacian or the D'Alembert?
No, it's antisymmetric because the adjoint of the retarded propagator is the advanced propagator. So just if you take the adjoint, just the role of advanced and retarded changes. And because it was a difference, it changes the sign.
I mean, delta is not the Laplacian, it's the commutator.
Oh, it's not the Laplace operator. Oh, I'm sorry, it's not the Laplace operator. I'm sorry, this is a convention. Yeah, it's just a commutator function. No. Okay, now this fact that this is the antisymmetric can be used to define the Poisson bracket of classical field theory, which is just the following, that the commutator, the Poisson bracket of fields at points x and y is just these, the integral kernel of this operator, so it's just this distribution delta of xy.
So is it integral on x, or is it like f of x and then they should be g of x, g of y, like in the second equation is the...
No, delta, okay. The convention is that here, oh, I'm sorry.
Well, delta G is already an integral, so it's a double integral.
Delta is an operator which maps the test function to a smooth function. And the result is again a function of x. Yeah, so it's but here I write delta of xy, which is the integral kernel of this operator. Okay, now I come to quantization. So we have the space of field configurations for a scalar field, and as this space we use all smooth functions, not only solutions, all smooth functions. And we define observables as functions on the space of configurations. Yeah, so
It's off-shell.
it's off-shell. It's a so-called off-shell formalism. Which is, of course, one could restrict oneself to solution space, but this is usually more complicated, and it's for the quantization turns out to be much more convenient to use the off-shell formalism. Yeah.
And maybe observables within quotation marks.
Okay. I don't want to discuss a measurement problem. Yeah, it's just I call it. It's just a name at the moment. Yeah, but I think it's actually. The observables are constructed in terms of these objects. Yeah, and how they can be observed is a different question I don't want to discuss. So these are just maps on this space of configurations, and of course they are rather huge set. So let us look at special cases. So, for instance, in Weidmann field theory, you are used to use linear functionals, so you just integrate the field phi with some test density f, and you can then of course multiply these functionals in the sense of pointwise multiplication, so you get polynomials, and slight generalization is to look at polynomials of the field in this way that you have the field at different points and you integrate it within test density in n variables. And another class of functions which is very important because the interactions are formulated in terms of these functionals are the local functionals. These are just defined in terms of a function on the jet space of M. And as a technical tool, we need differentiability properties of these functionals. So the notion of a derivative is very simple. Namely, the nth derivative is just defined as a directional derivative. And we call the function differentiable if this nth derivative defines a symmetric distributional density. And there is some further condition on the dependence on the field configuration phi, which I don't want to discuss, but I think this is nowadays a well-established framework of infinite dimensional analysis.
And psi is another test function.
Psi is, in this case, a smooth function. It's not necessarily compact support. But I assume that the functional derivative is a distribution with compact support. Okay, now I can extend the Poisson bracket to this space of this larger set of functionals by the following formula. So the Poisson bracket of two such functionals, capital F and capital G, is just given in terms of this commutator function integrated with the functional derivatives of F and G. And this has all properties of a Poisson bracket and was originally defined by Peierls, so-called Peierls bracket. Now we want to quantize this structure, so we use a concept of deformation quantization, which means that we look for an associative product which depends on a parameter h bar and which tends to the classical pointwise product, the limit h bar to 0, and the commutator divided by I h bar approaches the Poisson bracket. And there's a simple solution for this in this case, namely the Weyl-Moyal quantization, where you define the star product by this formula here. So you apply a formal power series of bidifferential operators to the product of functionals at different points, and then at the end you set phi 1 equal to phi and to phi 2. And this is to be understood as a formal power series in H bar, but of course, in case your functionals are polynomial, this is a finite sum. Yeah, so for the polynomials, this is an exact definition, but in the general case, this is only a formal power series. So let me describe it on a case of a linear functional. Then the star product is just the classical product plus, in first order in H bar, a term I times half of the commutator. Now, what is bad with this Wien-Moyal product in quantum field theory? The bad feature is that if you want to extend this product from the linear functionals to nonlinear local functionals, then you get problems. Namely, let me discuss it in the simplest case of phi squared. So phi squared integrated with a test density f is a well-defined functional. It's also differentiable. Everything is fine. But when you apply this formula, you get three terms. The terms without derivatives is just the classical product. Then you get the term with one derivative, which is okay. But then you get the terms with the second derivatives, and there you have to square this distribution delta. But delta is singular, and in general, products of distributions are not well defined, and actually, in the case of delta, you cannot help. There's no reasonable way of defining this square as a distribution. But now the positivity of energy helps us, as we know from ordinary quantum field theory. And we can also do this in this more abstract framework, namely we use the fact that this condition on deformation quantization do not fix the star product. We can replace the commutator function in this exponent by any distribution H whose antisymmetric part is I times the commutator function, because only the antisymmetric part is tested in the commutator. And if we do this, then we get a star product, which are called here on the slides the star H product, which is equivalent to the previous one. Namely, let us look at the operator gamma index H, which is defined as the exponential of H bar over 2 times this distribution capital H paired with the second functional derivative. And then, so this is again defined in sense of formal power series, and you can then easily check that the two star products, the original Wien-Moyal product and the star H product, are related by this operator, and also this operator is invertible, so this is really an equivalence of star products. But we would like to find a distribution H such that we can extend the star product to more singular functionals. So we have a certain wish list for this function H. So we require that it's a bisolution of the Klein-Gordon equation. This is just nice because then the functionals F which vanish on solutions form an ideal in this product with respect to this product, as in the classical theory. This is very nice because at the end we would like to go to the on-shell formalism where we divide out the ideal of functions vanishing on solutions. Then, in order to have a well-defined product also for local functionals, we want that pointwise products of these distributions exist. Furthermore, we would like to have something which is definitely wrong for the Wien-Moyal product, which can be required here. Namely, we require that H is a distribution of positive type, which means that if I integrate H with the test density F and this complex conjugate test density F bar, then you get always a non-negative number.
But H is not symmetric.
H is not symmetric, no. But
Well, this product is not symmetric, but okay. It's correct.
Actually, what enters here is the symmetric part of H, because you have the same function on both sides. Yeah. So that's really positive. This is a requirement. And what is the consequence? If you use such an H product, then you have the nice feature that you immediately get a lot of states. States on this algebra are functionals which are positive in the sense that they assume positive values on products of F bar F. And if you have this property, then you can easily show that every evaluation of this functional at a field configuration yields the states. These are just the coherent states. So this is a very nice feature of this.
It's a little bit like when you pass to a Kähler structure.
It's related to the Kähler structure. Yeah, that's true. And furthermore, I have this requirement on positive energies, namely, I want that this function H selects locally the positive frequencies. And okay, these conditions don't come from the sky. It's just what we already know from the two-point function in Minkowski space. So we just want to save as much as possible from the situation we know in Minkowski space. There, the Weidmann two-point function exactly fulfills all these conditions. And actually, this transition to this new star product just amounts to Wick ordering. It's just the Wick ordered version. Yeah?
Could you also select locally equilibrium, some kind of local KMS condition, rather than the positivity of energy?
Actually, the KMS states with positive temperature also satisfy this condition. So instead of the Weidmann two-point function, you could also use the two-point function of a KMS state. They have to fulfill all these conditions. So locally, there is no difference between the positive energy and the energy condition on a KMS state with positive temperature. Yeah. Okay. So now I can to discuss this condition, one uses techniques from microlocal analysis. In particular, one uses the concept of wavefront sets. So the wavefront set is a subset of the cotangent space. So the commutator function delta is a distribution on the product of the manifold with itself. And the wavefront set is then a subset of the cotangent space of the product of the manifold with itself. So there are two points of the manifold, x and x prime, and at each point you have a covector, k respectively k prime. And the wavefront set of delta, just because delta is a solution of the Klein-Gordon equation, can be shown to be of the following form. There exists a null geodesic connecting x and x prime, and this covector k is coparallel to the tangent vector of this geodesic at the starting point, and then you take a parallel transport of your covector to the other end of the curve, and you add it to the other vector, and this must give 0, so this is some kind of translation, invariance, or momentum conservation, if you want. This is the wavefront set of delta, and if you look at the wavefront set of the positive frequency part, it's just half of this, the positive half of this wavefront set. So you just have the additional condition that the momentum or the covector at the point x is future directed. And actually it's clear because the sum, if you have a sum of two distributions, the wavefront set is contained in the union of these two wavefront sets. So it cannot be smaller, yeah, because when you have this condition that 2 times the imaginary part of delta plus is just a commutator function, then this is the smallest possible wavefront set. Of course, you could also think of the negative sign in this relation. This would give the delta minus function, but delta minus, because of this minus sign, is not of positive type. So what you see is that these two positivity concepts, positivity in the sense of quantum mechanical probability, and positivity in the sense of the spectrum condition, the positivity of energy, coincide for the scalar field. I know of no fundamental reason why this must be so. Actually, this is a great problem in defining free fields on curved spacetime with half-integer spin higher than 1/2. So there you get a lot of problems. Because this positivity issue is usually not, there seem to be no reason that this is related, but for the scalar field it is related.
For the Dirac equation it works?
For the Dirac equation it also works, fortunately. Okay, now this concept of the wavefront set can then be used to define what is called a Hadamard function. This is due to Radzikovsky. And according to Radzikovsky, a Hadamard function is a solution, bisolution of the Klein-Gordon equation, such that the 2 times the imaginary part is the commutator function. And the wavefront set is just this positive half of the wavefront set of the delta functions. This is then called the microlocal spectrum condition, and H is of positive type.
But the waveform set is always pointing up in the future.
It's for the first entry.
Yes.
For the first entry, yeah.
But it's no space-like vector.
No space-like, yeah. It's actually it's light-like, but future-directed. Actually, this concept of the Hadamard function is older than the work of Radzikovsky, and you can just try to find more explicit form for the Hadamard function. So this form is given here. This is the form u divided by sigma plus v times log sigma plus w, where u, v, and w are smooth functions, and sigma is just the squared geodesic distance between 2 points. And what Radzikovsky proved is that his definition is equivalent to this definition. Actually, this definition has to be made more precise because you have to discuss the singularity in light-like and time-like directions. You have to say what happens if you are outside of a geodesically convex neighborhood and so far. So this is a very complicated definition, which was fully spelled out in a paper by Kay and Wald. And it's a major technical advance that this can be reduced to this simple property of the wavefront set. So this definition of Hadamard solution in terms of microlocal analysis makes it used a lot of things which could immediately be done. So first, this was a construction of Wick polynomials on curved spacetime as operator value distributions. So because you just compute correlation function of Wick product, everything can be done in terms of this distribution H and its derivatives. And you just have to see that all the products which arise are well defined. And this can be done in terms of the wavefront set. The condition is that the sum of the wavefront set of the factors never should hit the zero section of the cotangent bundle. And this can be it's just a consequence of this positivity condition on the covectors. For instance, in this way you can prove that in a Hadamard set not only the expectation value of the energy momentum tensor is well defined, but even the correlations are well defined. So if you want to understand the back reaction by looking at the expectation value of the energy momentum tensor, of course you have to also to look for the fluctuations, because otherwise the expectation value would be not of much use. Other aspect are the quantum energy inequalities, originally proposed by Ford, But Fuster found that this microlocal spectrum condition gives a very important generalization. Namely, what one finds is the expectation value of the energy density in a Hadamard set is not necessarily positive. This is already true for the energy momentum tensor in Minkowski space. But when you smear the energy density with a square of a real value test function, then it becomes bounded from below. And this can be shown in terms of these wavefront sets. And maybe the most important thing is that you can do, using these techniques, the ultraviolet renormalization of quantum field theory in curved space-time. And this was done by Brunetti and myself, and then completed by Hollands and Wald.
And what about infrared?
Infrared is a different issue. This is a different issue. Okay, so how is renormalization done? Now, the method is based on the concept of causal perturbation theory as originally proposed by Stückelberg and Bogolyubov, and then worked out in all details by Epstein and Glaser. So the basic idea is that you define the time-ordered products of Wick products of free fields as operator value distributions on Fock space, and you require that these time-ordered products satisfy a few axioms. And the most important is that the time-ordered product coincides with the operator product if the arguments are time-ordered. So what you would usually require. And then in the famous paper of Epstein-Glaser from 1973, they succeeded in proving that solutions satisfying the axioms exist and that the ambiguity is labeled by the known renormalization conditions. And then you can construct the solution either directly, which is in many cases somewhat complicated, or via some of the known methods, BPHZ, Pauli-Villard, momentum cutoff, dimensional regularization, or what else. Now we wanted to apply this to curved space-time. This required a reformulation, which only uses local concepts.
Before it was in the flat space.
This was in a flat space, yeah. Now if we do it on a curved space-time, so we cannot use all the techniques. So we have to generalize this a little bit. So we cannot have not this distinguished representation on the Fock space. So we do it space-free, yeah, without any reference to Fock space. We don't have translation symmetry, and we need a new concept of the adiabatic limit, because it just makes no sense to take the integral over all space-time if you don't know what the situation at the end of space-time is. And you need renormalization conditions which are in a sense universal. I will discuss what this means. Formally, what you do is you construct an operator called the time ordering operator, which is formally given by this formula. So you take the Feynman propagator associated to capital H, which is just H plus a multiple of the retarded propagator. And you have this pairing of this distribution HF with a second derivative. And okay, I omitted here factor H bar. Yeah, so you should think of a factor H bar in the factor of 1/2. And now the question is how, this is of course rather formal, so you have to see whether this can be made precise. And it can be made precise as a map from the set of multilocal functionals to the so-called microcausal functionals. Let me briefly explain what this means. So we have the local functionals. We restrict the local functions to those which vanish at phi equals 0, so the constant functional is not included there. And then the multi-local functionals is just this is just a unital algebra generated by the local functionals. And the microcausal functionals are those functionals where the wavefront set satisfies a certain condition. Of course, this explain this condition in detail is maybe a little bit too complicated at the moment. Just remember that it's a condition just made in such a way that the products which arise are well defined. Just as an example, so we apply this operator to a simple multi-local functional, which is just the square of two functionals of the form phi squared integrated with a test function. And then we have apply this operator, so we get three terms. Just the first term, which is a unit, then the first derivative and the second derivative. And the problem is again in the second derivative, because there we have the square of this Feynman propagator, HF. But the Feynman propagator is not a solution of the homogeneous Klein-Gordon equation. It's a propagator, so it contains the wavefront set of the delta function, which is just the diagonal. So the wavefront set of the delta function is just the diagonal xx. So 2 points should coincide, and the covectors have to add to 0. But
All dynamic space-like.
K can be arbitrary. All Ks are admitted. All non-vanishing Ks can be admitted. And then, of course, there is no positivity condition. And so when you define the square, you can add two covectors and you get 0. And this is just shows that in general, the square is not a well-defined distribution. But this holds only at coinciding points. So at non-coinciding points, you are always in the situation then that you can use these positivity conditions. So this product is well defined for non-coinciding points, but not for coinciding points. And this holds very general. And so what remains at the end, this is already in the framework of Epstein and Glaser, and the general case can be reduced to this, is the following mathematical problem. You have a distribution which is defined outside of a submanifold, and you want to extend it to the full manifold, and you use something corresponding to translation covariance on curved spacetime, which is a technical problem but can be solved. And so at the end, you get a distribution which is defined everywhere outside of a single point. And then you can discuss this extension in terms of the scaling degree, which was originally defined by Steinmann. So this is the following definition. You just scale your distribution by some positive factor lambda. You multiply the distribution by a certain power of lambda, and you ask that this sequence of distribution converges to 0 in the sense of distributions as lambda goes to 0. And as lambda goes to 0, yeah. And so you test the singularity as the origin. And the infimum of these numbers is called the scaling degree. And then the theorem is that if the scaling degree is finite, then extensions exist. And moreover, extension with the same scaling degree. And two such extensions differ by a derivative of the delta function of order scaling degree minus n. So in particular, if the scaling degree is smaller than n, then the distribution is unique. And if the scaling degree is infinite, then T cannot be extended. So this theorem...
I think this is due to Weil. Weil.
Yeah. Okay, I'm not sure who first gave a complete proof of this. So we were not able to find a complete proof. So it would be nice to know it.
I think André Weil proved that.
Ah, yeah. Okay. Also for submanifolds?
No, probably not.
Ah, yeah. Okay. Okay, so that's... so this theory replaces completely the standard regularization techniques. But in order to get a specific extension, they are often useful. And just to explain how this is related to standard regularization techniques, the following considerations. So let's assume we have a finite scaling degree, but larger or equal to the of the dimension. And then one can show that the distribution can be uniquely extended to all test functions which vanish at the origin of the order of the degree of divergence, which is just the integer, largest integer smaller than the difference of the scaling degree and the dimension. Then we choose a projection on the complementary subspace of the test function space. And then every extension is given by these formulas. So we just take the composition of the distribution with the projection 1 minus W. W is this projection on the finite dimensional subspace, and 1 is the unit operator. And all extensions are of this form. Now, such a projection has this simple form that it can be written in this Dirac-Bra-Ket notation as a sum over W alpha delta alpha del alpha delta. So the functions W alpha form a basis of this finite dimensional subspace, which is just dual to the basis of the distributions arising from derivatives of the delta function. So this means just that the derivative of W at 0 is the Kronecker delta times some sign. Now, assume we have some regularization technique. So we replace T by some sequence Tn. And we assume that Tn converges to T on the subspace of test functions which vanish at the origin. Then Tw was defined as this composition of T with 1 minus W. Now I replace T by Tn. And then I can apply Tn to both terms. So first I apply to the unit, and then I apply to this projection W. And what we see is that we can construct this distribution as a limit of Tn, where we subtract certain divergent multiples of the delta function or its derivatives. This shows how divergent counterterms occur in this formalism. So it's just because you have this projection, but you cannot split it for T itself, but only for the approximating sequence Tn.
So I guess there are two n's on your slide with different meanings.
Oh, I'm sorry. Yeah, here, this is the index of the signal. It's not the, I'm sorry, yeah.
And this is now all on Rn. It's not on a hyperbolic.
Oh, okay. So these ends are not related, yeah.
Yes. But your space-time is now an Rn, or what?
No. So this was just the general comment. Of course, this is some technical problem to reduce this problem of extending distributions on manifolds, which vanish on which are not defined on a submanifold, to the situation where you have just one point. So in a sense, you use some transversal coordinates near to the submanifold. Yeah, that's the way it can be done, but this is technically demanding. But I can, so this was done in this paper by Bonetti myself, and there's a recent PhD thesis by Viet Dang, who analyzed this from the mathematical point of view very carefully. But at the end, you arrive at this problem. But this, of course, requires some exercise in microlocal analysis. Okay, now we have all the means to construct these time ordering operators. So we look at the symmetric Fock space over the space of local functionals. So Fock space not just in the algebraic sense, so it's not considered to be a Hilbert space. Just the sum of symmetric tensor powers. And on this space, we have the multiplication map, which maps the space into the space of multi-local functionals. We define the n-linear maps Tn on the symmetric Fock space to the space of microcausal functionals just by using the this bidifferential operator in terms of the Feynman propagator, and because we go to several factors, we have to use the Leibniz rule, and this creates these indices ij here. So this gives all the combinatoric of Feynman rules and so on. And what is important is that this multiplication map turns out to be bijective. This is a little bit surprising because in the Fock space you have functions of different field configurations, and at the end you have functions of one field configuration. But due to the smoothness of the local functionals, so the local functionals are singular on the diagonal, but smooth along the diagonal. So they're singular transversal to the diagonal, but smooth along the diagonal. And this then allows to construct the inverse of M. And at the end, you can define this time ordering operator just by the direct sum of these maps Tn composed with the inverse of M. So this is a definition of T. And if you like path integrals, you can also formulate this as a path integral. Namely, it's just a convolution with the Gaussian measure induced by the Feynman propagator. But for the definition, this does not help because you have to do the same calculations. Yeah, so
But you give the formula.
but the formula is there, so you see the relation. Yeah, so it's just a different way of formulating this. Now we can define the time-ordered product. Namely, the time-ordered product is now just equivalent to the classical product by the time-ordering operator. With this formula written there. And so this is then this statement of this theorem, which of course contains as an essential point that this multiplication map is invertible. This was done together with Katarzyna Reisner. So particularly the time-ordered product can be defined as a binary product of functionals, and this product turns out to be associative and commutative because it's equivalent to the classical product. Then we can define the time-ordered exponential, which is just the exponential series composed with this map T. And by definition, T acts trivially on local functionals. This means that we define our functionals in the normal ordered form related to H. So if we change H, then we have also to change our functionals. Then we can define the interacting fields if we have some interaction L. And this is something one might call the Möller map from the freeze to the interacting theory. And this is just Bogle-Huber's formula for the interacting field. So we take the S matrix to the -1 product, the time-ordered product of the S matrix with the functional F. And this is well defined if T to the -1 of F is in this set of multi-local functionals. Yeah, so in general, there could be divergences, but for this set, it's well defined. Okay, then, as I said, there's some ambiguity in the definition of time-ordered products. And this ambiguity can be discussed in terms of the renormalization group in the sense of Stückelberg and Petermann. This is not exactly the same as the renormalization group of Wilson. So it's really a group. It's a group of all analytic bijections of this space of local functionals. And the crucial relation is that this is additive if these functionals have disjoint support. And the first derivative should be the identity. And then there is something which was called the main theorem of renormalization, an unpublished paper by Stora and Popinot. And okay, there are different versions of these theorems with different generality. And the statement is that if I have found such a formal S matrix, then any other formal S matrix S hat is obtained from the original one by composing it with an element of this group. So all questions of renormalization can then be deformed in properties of this group. So for instance, anomalies and so on can be discussed in terms of the group. Okay, now
This is in a curved space. Everything is in flat.
this is also in the curved space. Yeah, yeah. This is very general. Of course, in flat space, this is more or less what was known, but can be generalized to curved space. Now, there remains one ugly problem, namely, when one does this renormalization, one has to do it for every point of the space-time independently, because there is no symmetry in general. So how to compare these renormalization procedures at different points of space-time? And of course, there is some feeling how this should be done. So if you want to have an operation which is locally defined, but to make this precise is rather complicated. But of course, this problem does not exist on Minkowski space. There you have a sufficiently large symmetry. You can have other space-times with large symmetries where you have similar advantages. But in the generic case, you really have the problem that it seems that you have independent conditions at each space-time point, which of course would be very ugly. Now, the solution of this problem is to construct the theory not on one specific space-time, but on all space-times in a coherent way. And this can again be formulated in the language of algebraic quantum field theory. So we generalize the Haag-Hassler axioms in a useful way. So the idea is that we look at subregions as spacetimes in their own right. Of course, these subregions should be globally hyperbolic. And the generalization is the following. So we associate to every globally hyperbolic and contractible, orientable, and time-oriented manifold of a given dimension, a certain C-star algebra, or in perturbation theory, we restrict ourselves to star algebras. For every isometric causality at orientation-preserving embedding, we have an injective homomorphism of the algebra of the region M to the algebra of the spacetime N. And these, if you have two subsequent embeddings, then these homomorphisms just can be composed. And then we have some condition of local commutativity. So if these embeddings map into space-like separated subregions, then the corresponding algebras commute. And there is some dynamical law which just tells if the image of the spacetime M under chi contains a Cauchy surface, then A chi is even an isomorphism. So in the language of category theories just tells you that the quantum field theory is a functor from the category of spacetimes with admissible embeddings as morphisms to the category of unital star algebras with injective homomorphisms as morphisms. This is a concept which was called locally covariant quantum field theory, and in a paper together with Rainer Ferch and Romeo Bonetti. And in this framework, one can define a field independent of the spacetime. Namely, what is a field? A field is just a natural transformation between the functor of test function spaces and the quantum field theory functor. So this means you have a field phi as a family of maps, phi m, from the test function space of M to the algebra associated to M, and which transforms in the appropriate way under these embeddings. And so if you use this more suggestive notation here, you see immediately what happens if n is equal m, then chi should preserve the metric, so it's an isometry, so it's symmetry of the spacetime. It's just as the usual notion of a covariant field on a given spacetime. So this condition contains the usual notion of covariance, but it's valid in this more general framework. Now we can use this for renormalization. Namely, we define the time ordering operator as a natural transformation. And so this means if M is an admissible subregion of N, then the restriction of the time ordering operator to Tm must coincide with the restriction of Tn to the smaller subregion must coincide with Tm. There's a practical obstruction to do this. There's the fact that there is no natural Hadamard function. This is related to this problem that there is no vacuum state. And, but this can be solved, this problem, and the solution was in the series of paper by Hollands and Ward.
How do you mean it's solved? I mean, there is an ambiguity.
No, the non-ambiguity is there, but you have to isolate the non-ambiguous. So the ambiguity is there, but the singularity. So if you look at the form of the Hadamard function, there are some parts which are non-ambiguous, and there's the ambiguous part, and you have to show that what you do does not depend on the ambiguous part. Okay. Yeah. Okay. Actually, this is quite demanding. It's not an easy exercise.
And the Hadamard function means which kind of propagator?
The Hadamard function just means that you have a certain wavefront set. And then, but then I gave this explicit formula for the Hadamard function, which involved these smooth functions u, v, and w. And it turns out that u and v are uniquely determined by geometry, and w is free. And you have to show discuss the dependence on w. That's what you have to do. Okay, now up to now I discussed this on the level of scalar theories. Now we can generalize it to Dirac. Yeah.
So removing these ambiguities, does that mean we can say what we mean by when we say that the coupling constants of a quantum field theory are everywhere the same?
Yeah, so if you have a dimensionless coupling constant, this is everywhere the same, yes. Okay. This would be the statement, yeah. Actually, usually there remain some ambiguities. For instance, you have the coupling to the curvature, which can be tested, of course, only on a space with non-vanishing curvature. So if you start from Minkowski space, you cannot determine this constant. Yeah? So you have to, but this is a finite number of parameters in a renormalizable field theory.
But there would be constant psi.
Yeah, it would be a constant again. Yeah. Okay, so Dirac and Majorana fields can be discussed. This gives no fundamentally new problem, but you can make a lot of errors by making wrong signs and factors, and I think it's difficult to find paper where all these signs are correct. And but in gauge theories and gravity,
of phi, as Feynman would mention. Feynman never considered power of phi.
Yeah. Okay. So in gauge theories and gravity, one has new problems because the Cauchy problem is not well posed due to the gauge theory. And in classical field theory, you would just fix the gauge. In quantum field theory, you cannot do this directly because these things which you would like to vanish have non-vanishing commutators or Poisson brackets in the formalism of canonical field theory.
But can you just pass to Dirac brackets then?
Yeah, okay. That's the problem is with Dirac brackets is that the singularity structures are very difficult. So I think I know not any rigorous discussion of the Dirac brackets in this.
So you say that in passing from Poisson to Dirac brackets, you eventually potentially encounter a problem with singularities.
The problem is okay. I just don't know. So I have not found any place where this was treated in, say a sufficient generality. The problem is the following. All this in quantum field theory, at least in four-dimensional quantum field theory, you always have to smear over space and time. You cannot do smearing only in space. This creates singularities, but the concept of Dirac brackets is usually defined at a fixed time. And so,
I mean, it's really standard thing. For example, when we pass from Dirac to Majorana fermions, that gives you just a factor of 1/2, and that's
yeah. So for the linear fields themselves, this is okay. The problem is if you go to nonlinear fields, because then you get additional singularities, and I just don't know whether this can be done. Okay, but in Young-Mills series, we know how to do it using Faddeev-Popov ghosts and anti-ghosts. We have the BRST transformation. And just at the end, we define the algebra of observables as a cohomology of the BRS operator. And we can try to do the same for gravity. But in gravity, we have a problem. Namely, if we do this just in the same way as in Young-Mills, we find that the cohomology is trivial because there are no local observables. This is a major problem. It can, in principle, be solved in the following way. Namely, we use the dynamical fields themselves as coordinates. This, of course, is not always possible. This depends on the gravitational field. But for generic field configuration, this is possible. And so the idea is to...
Dynamic field, you mean on shell?
Not necessarily on shell, just generic in the sense that there are no special symmetries and so. So that you have enough independent, say curvature scalars, for instance. And then you just choose such a generally globally hyperbolic metric, and you expand then the extended action in around this up to second order, so you get a free field theory. One can show that this has Hadamard states, and then one adds the remaining term of the action, perturbation theory, and constructs everything. And this has to be done in such a way that the BRST invariance holds. And at the end, you prove that if you change the background infinitesimally, then the theory does not change. This is due to the principle of perturbative agreement proved by Hollands and Wald. And states can be constructed at the end by, if you start from a solution of the classical field equation and use this concept of coherent states around this. Okay, so I come to the end. So I've tried to explain how this functorial approach to quantum field theory works. This was originally developed for the purposes of renormalization on curved spacetime, but in principle it allows also a framework for a background-independent approach to quantum gravity. Of course, this does not change this problem of non-renormalizability, which means that you can perform everything step by step, but you get new terms in the Lagrangian in every order. So in this sense, it's non-renormalizable, but I think there's it's probably possible, nevertheless, to interpret this theory in the sense of effective field theory. At the end, actually, we have problems to see any effect of the quantization of gravity in experiments. So I think there's some hope that these effects are very small. So actually, this is supported by work on the renormalization group in the group of Reuter and others. And it's at the moment, the formalisms are a little bit too far from each other, but in principle, I think this can be compared to this approach of Reuter. There is one major lack in this whole procedure. There's up to now, no application to physical phenomena. And this is due to one ugly feature, namely the restriction to generic backgrounds. Namely, if you want to have an explicit example, you typically use not a generic background, but you use some with background which has additional symmetries, and then you cannot directly use these concepts. So in this case, you have to use other methods. So one way out would be to add certain fields, like, for instance, the dust fields of Brown and Kutscher, which have been used just for the same reason in loop quantum gravity. And but this is work which has to be done, which was not done up to now. Thank you very much for your attention.
Yeah, I have a question. I mean, this, as far as I understand, your approach relies very much on Epstein-Glaser.
Yeah.
Now, in quantum field theory, in practical quantum field theory, Epstein-Glaser is not used very much, but people use dimensional regularization and all. I mean, what would you advise? I mean, this is somehow related to the one but last point. If I actually want to do practical calculation, how should I proceed?
Yeah. Okay. So when you do it on Minkowski space, yeah, I think you can compare it only on Minkowski space, but on curved spacetime there's not much which was done in other formalism. Actually, I think no complete proof. I think the only proof for curved spacetime is in the Epstein-Glaser framework. But on Minkowski space, Epstein-Glaser is just equivalent to other methods. So you use the method which is most useful for you. So there are certain cases where this Epstein-Glaser method leads to shorter calculations, but there are also cases where it's more complicated. So I think I would actually what we analyzed was how to use dimensional regularization in the framework of Epstein-Glaser. This gives a position space version of the dimensional regularization, similar to what was already not really the same, but the spirit of some work of Bollini and Gambiaci. But you can also use other regularization methods. So that's not, yeah.
So I have two questions. I don't understand the last problem, but you know, maybe that's too technical. I don't know. The other question is there any kind of Wilsonian version of the renormalization group that I could use to analyze these field theories? Because naively it doesn't work, because usually Wilson needs momentum space, but maybe there is a more clever.
Yeah, so in principle you can actually, what you can do is you can replace what I call this time ordering operator. You could replace this by some more regular object. For instance, just by approximating the Feynman propagator by something regular. And then you get, you're just in this Polchinski version of the Wilson renormalization group. Actually, this has already been analyzed in a paper by us. So you really get the flow equation in this framework, but you can, you can use any approximation. So of course, momentum space makes no sense, but you can use just something. Yeah, that's just, which I think might be a problem for the interpretation, because you are free to use any. For instance, you can just look at a sequence of test functions which converges in the sense of distribution to the Feynman propagator, and then you.
Yeah, I mean, it's a related question in a sense, because for me it's not obvious that in general the renormalization group a la Wilson, the Wilsonian renormalization group, will be related to the renormalization group in the sense of renormalization of the theory, reduction of ambiguity, which are the free parameters, etc. Yeah. So in your case, what you define as a renormalization group is clearly a group acting on ambiguities.
Yes, yes.
Is there any way you could see that it has something to do with Wilsonian renormalization group and change of scale?
Yeah, you can see it, but the connection is not as close. Yeah, so what you can do is you can you can discuss it in terms of these okay. So what you can show is that in a certain sense, the Wilsonian renormalization group converges to the right thing. Yes, so you have you use some regularization, you get your regularized time ordering operator. You have your regularized formal S matrix. Then you compute an element of the Stöckelberg-Petermann renormalization group related to this transformation. And then you can show that in a certain sense these products converge. But I think the statements which exist at the moment are not very strong. It's related to the question whether this perturbative calculation of the coefficients in the renormalization group gives the right answer for the Wilsonian renormalization group. I think that usually in the calculation you usually neglect certain terms which you consider to be irrelevant. And I think that's the question how far this is justified. I think this answer has been given, to my knowledge, only in very special cases. Particularly only for renormalizable theories.
So that would be maybe the relation only exists for normalizable theories.
There exists a relation, but I think the problem is the relation, as far as I know them, are not very strong. There's some similarity, but it's not exactly the same.
Last question. In the case of quantum gravity, does your approach give a better definition of what would be a quantum back reaction than your G0? You say G0 is off-shell, whatever, but at some point you want a good G0 which incorporates back action.
Yeah.
Is there? Does it help or not?
Okay.
Frankly.
That's, of course, our hope. I think we are not so far. So we hope the formalism in principle should give it, but when we so what one should compare it is one should compare it with the so-called semi-classical Einstein equation. The semi-classical Einstein equation has a problem, a consistency problem.
It's experimentally shown to be wrong. There is a proof experimentally. Okay, let's maybe stop here because we want to go. Let's thank